Questions from the previous lecture? Are there any questions in general? Are we all happy? Okay, good to be happy. Mukesh, AC, air conditioner. The recording going on? Okay. Right, so recording's already started, so please behave yourself. So we'll start with the next lecture on system of particles, focusing on particularly the rotation of particles in this case. Okay, so towards the end of last lecture, we talked about the angular momentum about a fixed point O. And we also showed that the time rate change of angular momentum for a system of particles about a fixed point O is equal to the sum of torques of the external forces acting on the particles about the point O. Of course, I mean, for calculating torque, which is the moment of external force, you have to take the vector from point O to the point on which the force is acting. So if you have 10 particles, you take R1 cross F1, where F1 denotes the net external force on particle 1. Then you add R2 cross F2 and so on till R10 cross F10. Was that clear? So that was quite straightforward, and we were able to. So the idea here is that when we are working with system of particles, we want to see if we can generalize the ideas of single particle Newtonian mechanics to a system. And we were able to do that for the net external force. So we said the net external force acting on a system of particles is equal to the overall mass of the system, that is the sum of the masses of all the particles, times the acceleration of center of mass. So that tells us how the center of mass translates or moves for the system. Then we also talked about the work energy theorem. So we said that the net change in the kinetic energy of the system is equal to the net work done by all the forces, external and internal, on the system. Okay? So the net kinetic energy change, so the kinetic energy for a system was calculated as, or was found as, the half times m times v of center of mass squared. That's one component. That's how the system as a whole is moving. So you take 10 balls and the whole system is moving from this point to that point. So its kinetic energy as a whole is changing. All the balls, let's say, are accelerating. But the balls are also moving around the center of mass. To take that into account, we also added another term which was basically found out as a result of some derivation, that in addition to half m vcm square, we also have a term that is because of the relative motion of the balls or the particles around the center of mass. That was the next thing. And the third thing we did was we calculated angular momentum about a point O and showed that its rate of change is equal to the sum of the torques acting for external forces only. Internal forces for the torques due to internal forces, they cancel out as we showed. We'll start from there unless there is any question about what we discussed last time. There's one more thing we talked about. We talked about the net momentum of the system. So we said that the net momentum of the system, which is the sum of the momenta of all the particles, is equal to the overall mass times the velocity of center of mass. That's also a very important concept. In fact, if you want to generalize the ideas of physics beyond Newtonian mechanics, this idea also works. That's the beauty of it. But that is beyond the scope of my teaching here, that a physicist would be able to do justice to when you go to quantum mechanics or other ideas of physics, where you can still apply these ideas of momentum there. But still, for this discussion, we'll talk about Newtonian mechanics. So the next thing we'll talk about is calculating angular momentum about the center of mass. In many cases, we are interested to calculate the angular momentum about center of mass rather than a fixed point. So center of mass is moving, of course. It can have a velocity, it can have an acceleration, as we have seen. So we have defined a physical system that comprises many particles, and MI is just one of those particles. The center of mass of the system is denoted by G, and we also have a fixed point O that we are taking for reference. So when we calculate angular momentum of the system about point G, we'll have to take the contributions of the angular momentum from all the particles. So we sum over all the particles. And then since it's about point G, so we have to take the vector from G to the mass under consideration. So that's rho I vector. Cross the linear momentum of the particle. You have to be careful that the linear momentum here is the actual linear momentum, that is m times the velocity of the particle. You can write the velocity of the particle using the vector ideas as a sum of the velocity of center of mass plus the time rate change of the position with respect to the center of mass. So for the first term, I can move mi with rho I, because mi is simply a scalar. We're talking about cross product of two vectors, so we can take a constant on the other side. And this VCM can be taken out of the summation because it's nothing to do with the summation here. What is mi rho I summation? What is this? 0, right? So this term is gone. Let's compare the two red terms. So we started with calculating the angular momentum using the linear momentum, that is the absolute linear momentum. with respect to point O. That's how we define the angular momentum about point G. And we found out that we can also take the relative velocity of the mass with respect to point G. That is what rho I dot denotes. In this case, the absolute angular momentum and the relative angular momentum, they are the same. It doesn't matter when calculating angular momentum, you take the absolute velocity or the relative velocity with respect to the center of mass. Very interesting result, and that does not hold for a general point. We will show that in the second part of this lecture. That only holds for center of mass. This we discussed last time. So if you have confusion about why is summation mi rho I 0, then you have to have a confusion whether summation mi rho I should be 0 or not be 0. The coordinate system, I mean, what do you mean by coordinate system? We're talking about vectors here. The vectors are taken, so when we calculate summation mi rho I, then just to understand why this is 0, we say that let us calculate things from center of mass. It's worth writing that this is not true in general. This is not true in general for a point P that may be moving. The center of mass here is also moving. The next step is to see, because we defined angular momentum only so that we can use a dynamical relation that torque is equal to the time rate change of angular momentum. You have to check whether that holds still if we work with center of mass, if we calculate the moments about center of mass. So let's differentiate this expression with respect to time. If I look at my figure again, this one, so Vi is Vcm plus rho I dot Do we have a question here? If you would want to talk, you can go out and talk. There's no problem with that. You can excuse yourself and go out and discuss whatever you want, but please do not discuss it here. We'll upload the lecture after the class. If you want to see it after the class, if you have something more interesting to talk about and do, then you can still go out and do that, okay? Can we see that the first term here is 0? We just discussed that, except that you have d by dt as well, because we saw that mi rho I summation is 0. So d by dt of summation mi rho I will also be 0. Right? What about the second term? You can easily see that you have a vector cross the same vector, that is 0. So we are left with only one term, so this term mi times vi dot is simply the acceleration of the ith particle. Oh, sorry, it's the force acting on the ith particle, because vi dot is the acceleration of the ith particle. And we already know that the force acting on the ith particle, mass times the acceleration of the ith particle is the force acting on the ith particle. In fact, it's the sum of external and internal forces both, because we're talking about one particle. So its mass times the acceleration is the net force acting on that particle. But we already showed that if you have internal forces acting on two particles, then if you take the contribution of the moment of the internal forces when they are working in pairs on different particles, you see that you end up getting r12 vector cross with small fi. And since the internal force is from center to center, that's the kind of internal force we're talking about, and the vector r12 is also from center to center, so that contribution for a pair of internal forces will be 0. And since internal forces appear in pairs, so for each pair the contribution becomes 0. So without showing it again today, I'll simply write this as, where capital Fi is the external force. So rho I cross Fi is the torque calculated about the center of mass, because rho I is the vector from center of mass to the ith particle. And we'll simply write this as torque about center of mass for the complete system. That is going to be our notation if you are working with a system of particles. So we are happy that the dynamical relation torque about center of mass is equal to d by dt of the angular momentum about center of mass of a system of particles. And in the last lecture, we showed that torque about a fixed point O is equal to d by dt of angular momentum about a fixed point O. I have shown this for a fixed point O. So you are free to calculate, given the problem you have, calculate the angular momentum about any fixed point O and apply this relation, or calculate angular momentum about the center of mass and apply this relation. Can I now generalize it to any point P that is not fixed? No. We will show that that is not the case. So please do not take and apply this dynamical relation about any point P if that point is not stationary, because you will see that you get extra terms. In fact, when we worked with single particle, if you remember, I wrote an expression where you had a contribution because of the motion of the point P as well. So we'll derive that for a system of particles today, and that is going to be a bit intense. We'll have lots of terms and playing around. So if you get confused, you can stop me and I can slow down a bit. But before that, let's do a problem. So we have three masses. They are connected by rods which are welded at point O. These three rods are almost massless, so you can assume their mass to be 0. So the mass for the system is only contributed by the three particles of mass m each. And this the arrangement of rods is symmetrical about the center. So the angle is 120 degree each. Now what we are doing is, we are applying a force F at this instant at a distance of B from the center, and the radius of the rods are equal to R. So we have to find the acceleration of the center of mass. In this case, that is actually O, the point, and theta double dot for the frame. Now before we even jump into solving the problem, let's have some intuition. Do you think that this whole system will move or translate from left to right? There's no friction from the floor. Do you also have an intuition that this system will start rotating? Good. So let's now apply. It's a system of three particles. So our first attack should be using system of particles. We already know that the sum of all external forces, that is capital F, is equal to mass of the system times the acceleration of center of mass. It's a welded joint, and the particles, the way they are, the center of mass is at O all the time. Center of mass, the relative particles are not moving with respect to each other, so the center of mass is O. So the only force acting is F in the I hat direction. The mass of the system is 3m, and acceleration is what we have to find for center of mass, which is nothing but the point O. Now the next is we have to find the angular acceleration of the frame. It makes sense we work with the torque relation. In this case, you have to choose whether you would want to calculate the torque or the angular momentum about a fixed point or the center of mass. So we will choose the center of mass, because we just now proved that torque about the center of mass is equal to d by dt of the angular momentum about center of mass. I am using g here because let's use g everywhere, that's easier. Because point O in our convention is a fixed point, so that may be a bit confusing. there's only one external force, and this torque is because of the external forces acting. About the center of mass, the torque is F times B, and what is the direction? The clockwise torque, and since anti-clockwise is taken as positive, so this becomes minus F times B times K hat. Now the angular momentum about G, we said we can use any expression, either the absolute angular momentum or the relative angular momentum. In this case, it's easier to calculate the relative angular momentum, that is with respect to the center of mass G. So that is rho I cross mi times rho I dot. So rho I is the vector from the center of mass to the ith particle. Now I do not know how the particles will, how the system will rotate. So what I do is, my convention says that theta dot and theta double dot in the anti-clockwise direction is positive. So in case it rotates clockwise, I will get the answer as a negative value. So I will simply multiply everything by 3, because I know that each particle is contributing the same angular momentum because of the symmetry. So for one particle, what is rho I dot? R theta dot, right? You can go mathematical, you can work with the expression of velocity in the r theta coordinates. So you call this as r and this as theta if you are working with the top particle. You can see that the r hat component of velocity is 0 because the particle cannot go away from the center. The only thing it is doing is rotation. It has a tangential velocity, that is r times theta dot. Sorry, what was the direction of the angular momentum? K hat. When I differentiate this, I see that it's only theta dot that changes with time. R, M and K hat, they are all fixed, they do not change with time. This is the angular acceleration, and it's negative because anti-clockwise was taken as positive. So that means the actual angular acceleration is clockwise, and that is what we had the intuition when we saw the problem. Any questions? have you studied this angular momentum about center of mass? Just asking. We already have discussed that now with the problem, but just as a baseline, have you studied this system of, you have studied system of particles, I know that, because that's, you know what center of mass is and how to calculate that for even rigid bodies. But have you studied angular momentum about center of mass? You have used that in the past? Now this I'm sure you have not used. Angular momentum about a point P that may be accelerating. Because this is rarely done, but there are some situations where this may actually become useful if you know the acceleration of point P, about which you are calculating the angular momentum. Anyway, so let's get into it. So I will need your full attention here, because if you lose me somewhere in these steps, then you will have lost the whole half an hour later. Okay, so please concentrate. In this case, what we do is we take a green point P, central point, we will call it rho I prime. So rho I was the vector from the center of mass to the ith particle, and rho I prime is a vector from the point P to the ith particle. And the position of the center of mass from the point P is rho Cm. We have used the same convention Cm because we had used RCm for the vector from the fixed point O to center of mass. And this is our convention. We are interested to calculate L about point P. So we will sum the contribution of the angular momenta from all the particles. So for the ith particle, the angular momentum about point P will be the vector from point P to the mass mi, that is rho I prime, times its linear momentum, that is mi times vi. What I am trying to do is, I am trying to, rather than working from P to the mass, I am trying to work from G to the mass. That is the center of mass to the mass. That means instead of using rho I prime, I write things in terms of rho I. So I can use rho I prime is equal to rho Cm plus rho I. So now the mass is approached from the center of mass, because I already know how to work with L about G. What is this second term? That's the angular momentum about the center of mass. The absolute angular momentum. Summation MIVI is nothing but m system times velocity of center of mass. Let's understand this final expression. The center of mass, sorry, the angular momentum about point P, a general point P, is equal to the angular momentum about the center of mass plus rho Cm cross MCm. So what is rho Cm? Rho Cm is a vector from P to the center of mass, and MCm is the linear momentum of the system. So if you have lots of particles, you can say that the linear momentum of the system is the overall mass times the velocity of center of mass. So you can assume that there was one particle concentrated at the center of mass, and the angular momentum of that particle is added to the angular momentum of the about the center of mass. Any questions? Well, that was the first half. The second half is to now differentiate this with respect to time. Can you please stop giggling and chatting? I please request you, okay? It's only 1 hour. You are coming to the lecture by your own will. If you want to giggle, you can go out. Because it's a bit disturbing, so I lose my chain of thoughts, and that affects the whole lecture. So let's differentiate this LP with respect to time. And this VCM dot is nothing but the acceleration of center of mass. Now, is this thing equal to tau p? We don't know. If we already knew this, then we will not do this exercise. We will simply say tau p is equal to d by dt of LP. But that is actually not the case. That is what we are trying to show. If you want to see what is the relationship between tau p and d by dt of LP, that's the aim of this discussion. So we'll separately calculate tau p and then see how they are related, 1 and 2. So what's the net torque about point P? It's a summation of the moment of the forces about point P. Again, I am only taking external force. Now we are experienced with how to get rid of internal forces as pairs when calculating moments. And this time we have a rho I prime because we are taking things about P. So let me go to the figure. So rho I prime is a vector from P to the mass. Again the same thing, we will want to work with from center of mass to the mass, ith mass. What is the second term here? Right? The torque about the center of mass G. Can we write this? If I move the summation over Fi, that becomes the net external force on the ith particle. That is, I mean, the total force on the total external force on the system. So summation Fi becomes m times acceleration of center of mass. The angle between rho cm and VCM. Where is VCM? Or the equation. So we are not, so this is not from equation number 1. That's an independent expression. So you are asking when we differentiated LP. We are not ignoring any angle. I think the confusion is how we differentiate a cross product. So differentiation of d by dt of A cross B is d by dt of A crossed with B and A times d by dt of A cross d by dt of B. That is the property of cross products and their differentiation. So that is something I can discuss after the class with you. So please ignore that question. That has nothing to do with this calculation of torque. Okay. So this is what we have found in terms of the expression for torque. Let's call this So I'll have to zoom out a bit to see 1 and 2 both. So my aim is to relate tau p with d by dt of Lp. So let's do that using 1 and 2. What we have is d by dt of Lg, and that term exists in 1, and we have rho Cm cross m ACm, that is also existing in 1. So this becomes okay. So that's simply using 1 and 2. It is not too elegant. We'll want to clean it a bit. Now rho Cm can be written in terms of RCm and RP. The point P's motion is something that may be known, and that is the whole reason we are doing all this. If we do not know how point P is moving, there is no point calculating the angular momentum in torques about an unknown point. In a problem, we will want to take a point whose motion is known. Yes, please. Now, we will come to this analysis once we have an expression in place. Okay. So we'll write rho Cm in terms of Rp. So I would want to write it in terms of Rp. So I can write my rho Cm as Rcm minus Rp. So this is how we relate tau p with d by dt of Lp. So we see that there is a contribution here because of the velocity of point P. It does not talk about acceleration of point P. It's only velocity that is required. Even if point P is moving without accelerating, and this, in fact, I had written the same, very similar expression for a single particle. And I had told you to prove it yourself. And I have proven it for a system of particles. So proving it for one particle becomes now trivial. Now, whenever you develop a more general expression, a sanity check is you try to apply it to a particular case. Of course, it is general. I mean, that is not a test. That is just a sanity check whether it works for a simple case, because it's a general expression. It may or may not work for other cases, but that's one check we can do. So can we check if my point P actually becomes a fixed point do I still get the expression tau O is equal to d by dt of LO? If my point P is fixed, then Vp becomes 0. Is that right? So that we get the expression tau naught is equal to d by dt of L naught. But this is more general. So there is more to it. So till now what we did was we calculated LP in the absolute sense. That is, it was rho prime cross MVI. We can also calculate LP in a relative sense, where instead of VI you have rho I prime dot. And we will see that the expression changes, because for center of mass I told you that the angular momentum about center of mass taken in the absolute sense or the relative sense is the same, but that is not the case for a general point P. So we will, in the next lecture after the quiz, we will talk about how to calculate this, what is the dynamical relation between tau P and d by dt of LP in a relative sense, and that will be the end of this discussion on angular momentum, and then we move to variable mass system. So next lecture we have a quiz. Now the quiz will have two questions. They will be printed on a piece of paper and given to you, and you have to solve both. So in case you cannot solve one, then you can solve the other one, or if everything goes well, solve both. There will be simple problems, so keep your mind open, and the syllabus is whatever we have done after quiz 1 until today. Thank you.